Our video today is on electron configurations. It's just another way to describe the modern atom, this time using numbers and letters. And we can use our box diagrams, which we learned in last video, to kind of help us figure out the electron configurations. So you can take out problem book page 303, and if you need to pause the video, you can, because we're just going to go back to what we did last time. So to refresh your memory, here we have our box diagrams from before. And here we had boxes which represented orbitals and arrows which represented electrons. And we learned that electrons filled the lower energy level before they moved up. We also learned that you could only have 2 electrons in an orbital and they had to have opposite spins. We also learned that when you had an orbital like 2p that came in sets, so 2p's come in sets of 3s, that the electrons filled one orbital at a time before they started to double up. It's kind of like children in a room, they each get their own room, but when they're out of that energy level, they have to start doubling up before they go to the next one. And so we're going to take this box diagram and turn them into electron configurations, which is even easier than the box diagrams, I think you'll find. So let me show you how to do that. So here we have an arrow or an electron in the 1s orbital. So I just say 1s, 1. So that represents the 1s orbital and 1 electron. So the superscripts are the electrons. Helium has 2 electrons in the 1s orbital, so I say 1s2. Lithium has 3 electrons, but they're not all in the 1s orbital. Only 2 can go in the 1s orbital, and then one of them is in the 2s orbital. Go down to beryllium. We have 1s2 and 2s2. So I'm sure you're seeing the pattern. And if I just count the superscripts, I can go back and figure out how many electrons. So 2 and 2 is 4. There's 4 electrons in beryllium. Let's try something farther down. How about oxygen? So oxygen has 2 electrons in the 1s orbital, 2 in the 2s orbital, and 1, 2, 3, 4 in the 2p orbital. So that becomes 1s2, 2s, no, let's start over with that one. 1s2, 2s2, 2p4. And that mistake reminds me that these are all little letters. So this is not a capital S. So this is small letter s and small letter p. So this is 1s2, 2s2, 2p4, and these are superscripts. So that's the pattern. I think you can follow that. And go ahead and pause the video and fill in the rest of page 303. All right, hopefully you did that and you're back. What if I wanted to do an electron configuration, but didn't do a box diagram? I just wanted to do it given an element. So here we have the periodic table. All right. And what if I wanted to do phosphorus? So I can see phosphorus, or maybe you can't see very well on the screen, but phosphorus is 15. And so it has, the neutral atom has 15 electrons. So what if I want to do the electron configuration for phosphorus, but I don't have a box diagram? I'm going to go straight from the periodic table to the electron configuration. What can I do? Well, you can go back to page 213 where we talked about the modern atom and the sublevels. And you can remember that we fill up the lowest energy first. So I'm going to fill up the 1s, then I'm going to fill up the 2s, then I'm going to fill up the 2p, then I'm going to fill up the 3s, then I'm going to start filling up the 3p. So I can use this diagram to see. This was Bohr's first circle, this represents Bohr's second circle, and this would represent Bohr's third circle around the nucleus. So I'm going to fill in the 1s, then the 2s, then the 2p, then the 3s, and then I'm going to start on the 3p. So I have to get up to 15 electrons. So I go 1s, and the s orbitals can hold 2, so it's going to fill the 1s first. Then it's going to go to the next layer, which is the 2s, and s's can hold 2, so I put 2 there. Then the 2p's come next. So I go to 2p, and you can now fit 6. 6 electrons can go in the p, all right? So I have 6, 7, 8, 9, 10 electrons so far. So I'm not there, I need 15. So what comes after 2p? Well, if you look at that chart again, the 3s is next. So I go to the 3s level, and I've got 2. So I have 6, 7, 8, 9, 10, 11, 12. I'm almost there. I go to the 3p next, because that's next on the list. So I go to the 3p orbital, but I only need 6, 7, 8, 9, 10, 11, 12. I only need 3 more electrons, excuse me, to add up to be 15, okay? So I go 3 here. This 3p orbital can hold up to 6, but no more than 6, but it can hold less than 6. It can hold 0 or 1 or 2 or 3 or 4 or 5 or 6. So now I have this configuration done. So this is for phosphorus, which is element 15. And I have 2, 4, 10, 11, 12, 13, 14, 15 electrons. And so I have my electron configuration without doing the box diagrams first. And life would really be simple if that's all we needed to know. But it starts to get even more complicated. We know that the modern atom has a lot of complication to it, and this is one of them. So normally we would think you'd fill in the 1s, then the 2s, then the 2p, then the 3s, then the 3p, and then the 3d, but that's not correct. You actually fill in the 4s next. So why? Why does that happen? What's going on? Well, you have to go back and remember that back in Bohr's idea, there was the first energy level, then the second, then the third, then the fourth, and the fifth, and that's still true for the modern atom. But the first energy level has 1 sublevel, second splits into 2, the third splits into 3, the fourth splits into 4, and so what happens when they split? So they used to be at 1 energy level and they split. So look at this. First energy level is the 1s. The second energy level splits. Okay, it used to be here, but it splits into the 2s and the 2p. The 3 splits into 3, 1, 2, 3. But the 4 splits into 4, and now we have this kind of, using my fingers, this overlap. So the lowest 4th energy level is actually lower than the highest 3rd energy level. And then it goes, so here's the order that it goes in. We fill the 1s, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then the 3d, then the 4p, then the 5s, then the 4d, then the 5p. How are you going to remember that? Well, fortunately, we do have a way that will help us out. And that's the periodic table. Periodic table is your friend. So how are we going to use the periodic table to figure out this order so I don't have to memorize 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f. Oh, crazy, crazy. So how am I going to use the periodic table to help me out? Glad you asked. Well, you may have noticed when you looked at a periodic table that it's not just a box, okay? It has kind of this high tower over here. Then it has this kind of shorter tower in the middle, which is long. Then it has this section over here. And then way down at the bottom, it has these 2 long rows, all right? These actually have to do with the orbitals, which affect the properties, which affect the periodic table, which we'll learn about this week. So you may notice that this high columns over here come in 2. So if we go back to our chart, what kind of orbital can hold 2 electrons? Well, look, the s orbitals each can hold 2 electrons. Well, we have 2 columns here, and guess what? We're filling the s orbitals here. What about this section over here? I have 1, 2, 3, 4, 5, 6 columns in this region. Let's go back to our chart on 213. What comes in a set that fits 6 electrons? Well, the p orbitals can hold 6 electrons, all right? So all p orbitals can hold 6 electrons. That's the set of them. So together, all the p's hold 6 electrons. So this represents where the p orbitals are filling in. Okay, I think you're going to notice the pattern here. So this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What type of orbital can hold 10 in its set? Well, that's the d orbitals. So this is where the d orbitals fill in. Okay? And then at the bottom, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And what can hold 14? Well, sure enough, our f orbitals can hold 14 electrons. So our periodic table can tell us where the next orbital comes. These represent the s, these represent the p's, these represent the d's, and these represent the f's. All right, so I've marked a periodic table for you. But I want you to get out page 307 so you can mark one up to have. So you have a blank periodic table on page 307. So take this out and mark it with me. So here's our blank periodic table, which I've marked up. Okay? So we call these rows. Okay? And these equal the energy levels for the S's and the P's. So when I'm going here, I'm filling up the s orbital, the 1s orbital. And notice here we got helium, which is kind of the exception to the rule because it's more like over here when we talk about electron configurations. So there's a little bit of an exception. So we have the 1s. Then what comes after the 1s orbital in our chart? The 2s orbitals. And then comes the 2p orbitals. And then comes the 3s orbitals. So I'm moving left to right. Then comes the 3p orbitals. Okay? So I'm in the 4th row. Then comes the 4s orbitals. And what comes after the 4s orbitals? The 3d orbitals. Remember, because of the overlap, the 4s is slightly lower than the 3d. So 4s and 3ds. Also notice the number in front of the d's is 1 less than the row. Okay. So this is the row -1. So these are the 3rd energy level, 3rd D, 4th D, 5D, 6D. Okay, so it's 1 less than the row. This is in the 1, 2, 3, 4th row, but it's the 3Ds. And then down here we have the F's come in, and they come in right here where there's a star, and this one comes in down here. So if I want to know the order, I can go left to right on the periodic table. So the 1s fills first, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then the 3d, then the 4p, then the 5s, then the 4d, then the 5p, then the 6s. Oops, now I have to go down here. Then the 4f. And notice the 4 now is 2 less than the row it's in. So this is row 6, but the F's are 2 less. So 6S, then 4F, then 5D, then 6P, then 7S, then 5F, then 6D, and we have the periodic table. Wow, amazing. So let's say I wanted to find the electron configuration of this element right here, right here. And if I looked on the periodic table, I would see that was gallium. It's blackened here, and it's number 31 on the periodic table, so I have to have 31 electrons. So let's say I wanted to do the electron configuration for this atom right here. So now I'm going to use my periodic table to do that. So it fills in the 1s energy level first, and we can fit 2 in there. Then what comes next after 1s? Then the 2s comes in. And I can put 2 in there. Then after the 2s, I fill the 2p orbitals. So 2p, and I can put 6. 1, 2, 3, 4, 5, 6. So what comes after 2p? The 3s. What comes after the 3s? The 3p. And notice, because they're full, I know that there's 2 in S's when they're full. There's 6 in P's when they're full. Now I go down. I'm at the 4S level. Then I go to the 3Ds, and the 3Ds can fill in 10 I didn't do much planning, so I'm going to have to draw this pretty small. So after the 3Ds, I come the 4p, but I need to stop right here. This is the electron. This is the element I want. So how many p's did I fill in? Just one. This is one. So this is the 4p1. So there we have it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. And how many electrons is that? 2, 4, 10, 11, 12, 18, 19, 20, 31. And gallium has 31 electrons. So if you mark up a periodic table, and you'll notice an easy pattern: S's, P's, D's, and F's. The S's and the P's are the same energy level as the row they are in. The D's are one energy less than the row they are in, and the F's are two energy levels lower than the row that they are in. So give those a try. Hope you do well.